Hello and welcome to a new lecture on discrete mathematics. In today's lecture, we are gonna learn about functions. Very easy topic and you are already aware of it. So in here we start studying some basics on functions and then we try to do coding. So function is a process which receive some input and give us some output. And in between here, there is some performance or some action is done on input. Computer systems are also kind of function. They receive some input, they process, and they give us some outputs. So if we have two non-empty sets like A and B, then we define a function of f from A to B, which is defined as assignment of exactly one element of B to each element of A. We write it as fa equals b, or you can say fx equals, for example, x2 plus 1, or y equals to x2 plus 1, right? Or fa equals b. In here, b is the unique element of set B, which is assigned by a function to an element of A. So here you can see one example that we want to do, or we want to assign grades to students. In here, we can see that we have a set of students. For example, this is set A, and this is possible grades that we can assign to each student, set B. Each student must have a grade for a special course, not for all courses. This is for only one course. One student must have a grade, and one student cannot have more than one grade. So Joe got A, Kim got B, Lee got B, and Park got C. It's okay. It's a function. But here, Joe got A, it's okay. Kim got B, is okay. Lee got B, is okay. But Park cannot get both C and D. That's why this is not a kind of function. For one course, one student must have a grade, but not more than one, only one. Functions are sometimes called as mapping or transformation. If we create a mapping for a student, like if a student to grades, we can rewrite as fa to b, like f of Joe is grade A. So this comes from set A and this comes from set B. Joe got A, Kim got B, Lee got B, and Park got C. It's a kind of function. Also, we have some other functions, as you know. For example, fx equals to x2. What it means x is an input here, and x squared is output. Like what we have seen here. We give x as input here, and our output is x squared. For example, if we give 0, the output will be 0. If we give 1, the output will be 1. If we give 2, the output will be 4. If we give minus 1, it will be 1. If we give minus 2, it will be 4 again, right? So this is a kind of function. A function f that maps A to B can also be defined as a relation. We already know that a relation is a subset of Cartesian product. This subset is restricted to be a relation where no two elements of relation have the same element. Specifically, a function from A to B contains one and only one order pair of A and B, or you can see here x and y for each element A in A in A. So for all x, where x in A, there exists y, where y in B, and in the Cartesian product of 2. Or you can say, for all x and all y1 and all y2, xy1 in F and xy2 in F implies y1, y2. Let's review some definition for functions. Look at the figure here. This figure is a function which maps from this set A to set B. For example, one element of A is mapped to FA here. So if we have this function, for example, f maps A to B, or we can say f is a mapping from A to B. Mapping from A to B. In this case, A is called as domain. This A is called as domain, and B set is called as codomain of function f. If fa equals to B, then B is called as the image of A under F. Image of A under F. And A is called as pre-image of B. The range of f is the set of all images of points in A under f of A. Two functions can be equal when they have the same domain, the same codomain, and map each element of the domain to the same element of codomain. So 1 same domain, 2 same codomain, and 3 map each element of the domain to the same element of codomain. Then we call them as equal functions. Suppose we have a function of f student to grades, as we already explained. We say f maps a student to grades, or we can say f is a mapping from a student to grades. In this case, a student is called as domain of function f, and codomain grade is called as codomain of f. For example, if Joe got a grade, then a is called as image of Joe under f. A is the image of Joe under f. Joe is the pre-image of A. And the range of f is the set of all images in student under function f. Range f student A, B, and C. Let's see one example here. We have a function which receives x and give us 2x plus 1. In here, as you can see, this is our function. This is A and this is set B. So domain of f, if this is fx, domain of fx is 1, 2, 3, 4, as you can see here. And set b, so this is set A and this is set B. Set B is called as codomain. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The range A, when we give 1, 2 multiply 1 plus 1 is equal to 3. 2 multiply 2 plus 1 is 5. 3 multiply 2 plus 1 is 7. And 4 multiplied 2 plus 1 is 9. So this is called as a range of function 3, 5, 7, and 9. Functions may be specified in different ways. Explicit statement using a formula or computer program. Here you can see an explicit statement of assignment, student, and grades. We have a set of students, we have a set of grades. Each student must have a grade. Each student cannot have more than one grade, and grade may be assigned or not assigned to a student. This is a kind of explicit statement of a function. We make a formula. Fx is equal x plus 1. Fx equals x squared. Fx equals sine x. Fx equals ln x. Anything, right? Or using computer, we already did it, right? A Python program that when give an integer, that it produces and it gives us, so we call it, we send some argument and it processes it and it may return something to us. Whenever we need the function, then we can simply call the function by sending some parameter to functions. So these are 1, 2, and 3 ways that we can define functions. So here is an example. We have a set of A and a set of B, right? So what is f of A? A in here is assigned to Z, so Z. What is the image of D? D is assigned to Z, so Z is the image of D. What is the domain of F? A is the domain of F, which is equal to A, B, C, and D. What is codomain? Codomain is X, Y, and Z. What is the pre-image of Y? B. Pre-image of Y is B. What is FA? FA, Y, and Z, because we have only 2 possible. X is not assigned. And what is the pre-image of Z? Pre-image of Z are AC and D. AC and D. Here is another example. If we have a function of f which map set of A to set of B, and if S is a subset of A, for example, S is B, C, D something, then Fs such a way that S is in S, then we have A, B, C, right? A, B, C goes to Y and Z. Y and Z. Suppose this is a subset. Suppose S equals to A, B, and C, and S is a subset of A. Right? Then F, C, and D give to Z, as you can see here. We have several types of functions, namely injections, surjections, and bijections. Injections functions are known as one-to-one functions. Surjection functions are called as onto functions, and bijection functions are called as one-to-one correspondence. So let's study them with some example one by one. Injective functions are defined if we have function f. F is one-to-one or injective if and only if FA is mapped to FB, right? It implies that A equals B for all A and B in the domain of F. So you can see here 1 to 1, right? No more than 1. This is called as 1 to 1. A function F is called surjection or surjective or onto. This is called as 1 to 1. Onto if and only if for every element of A there is an element of B. So may you ask, what is the difference between injective and surjective? An injective function is one which each element of A is transferred to at most one element of B, at most one. But a surjective function maps each element of A to some and at least one. In the previous one, it must be 1. In here, at least 1. It means 2 can go to 1 also. But in here, 2 cannot go to 1. And a function f is called as a bijection or called as one-to-one correspondence if it is one-to-one and onto. It means it's a composition of surjective and injective. As you can see here, this is bijection. So let's see examples. Here, in this one, this is one-to-one, but it is not onto. Why? Because we have no mapping to 2, right? No mapping to 2, but as you can see here, A is mapped to 3, B is mapped to 4, and C is mapped to 1, right? But it is not onto. This is 1 by 1, but not onto. Then we have here, this one is one-to-one and onto. Why? Because it's a complete mapping from set A to set B, and each element has a corresponding mapping. We have no 2 and all are mapped. This is called as both. You can say bijective. This one is not one-to-one, is not onto, is not bijective, and it is not a function. Why? Because A is mapped to 2, right? And we said one student can't have 2 grades for one course. That is not a function. Number 4, onto and not one-to-one. Why? Because here 2 students are assigned to 1. This is not one-to-one, but it is onto. And the last one, this is not one-to-one because A and C are mapped to 2, and also 4 is not mapped. So because A and C are here and 4 is not, so that's why it is not one-to-one and it is not onto. We want to show that a function is one-to-one or onto. For example, we have f function which gives us from a, b, c, d as set A to 1, 2, 3 as set B. And we say that it is like this. A to 3, B to 2, C to A, and D to 3. So what is this? One-to-one or onto? This is an onto function because all 3 elements of codomain B are imaged to some in A. If the codomain we change it to 4, then it's not onto-on. So we do this one. It is not one-to-one because A and D are assigned to same element of 3. So this is onto, but it is not one-to-one. How about a square function? Is it onto or not? A square function is this one. What is this? This is onto or not? This is not onto because there is no integer that goes to -1, for example. We can say x squared equals to -1. That's why for set of integers, it's not onto. If f squared is one-to-one or not, again not, because, for example, f1 is equal to f minus 1 equals to 1. As you can see here. That's why. So f squared is not onto and is not one-to-one. We have inverse functions. So if f should be a bijection from A to B, then the inverse of f we show by if inverse like this. F inverse is if this is our f, then f inverse is y of x, right? as you can see here, if this is A and this is B, if FA is this one and FB is from B to A, the opposite direction. Here is some example of inverse function. It should be noted that no inverse function exists unless it is bijection. It must be. So if inverse function, we should be 1 to 1 and onto. For example, there is no inverse for x squared because it is not 1 to 1 and on. So because other functions are not invertible, only a bijection function is invertible. As you can see here, these arrows are this side. It means we are mapping from A to B. But in here, you can see the arrows are from this side. It means we are coming from B to A. Here, we are going from A to B. That's why I call that inverse, opposite direction. Let f be a function from R to R where fx squared is invertible or not. As I said, it is not because f of minus 2, for example, is equal to f2 equal to 4. This is not 1 to 1. If an inverse function were defined, it would have to assign 2 elements to 4. That's why it is not invertible. Example, suppose we have a function of f which maps from A to B, and A is ABC and B is 1, 2, 3. So if f of A is 2, fb is 3, and fc is 1, is f invertible? And if so, what is the inverse? So this function is invertible because it is 1 to 1. So you can see it is 1 to 1. That's why it is invertible. And the inverse function is opposite side. In here, we say f of A equals to 2. If we here, we say f inverse of 2 is A. In here, we say f of B is 3. In here, we say f inverse of 3 is B. In here, we say fc is equal 1. And in here, we say f inverse of 1 is C. Composition, function of function. You can say function of function. Previously, we say fx. X is variable, right here, variable. But instead of x, we have another function. This is called as composition. And we show like this, FOG, f of gx. As you can see here, we have like this is one, A, B, and C, right? So f, in here, A is using g, function g. And in here, we have FOG from here to here, right? FOG which maps A to C, and in between here we have a function f which maps B to C, and g of fx is this one, as you can see here. So composition is instead of x we have another function. You can say this is as cascade. Cascade means input of a function is the output of another function. This is called as cascade or composite. Here you can see we have a set of A, we have a set of B, and we have a set of C. So G maps A to B, F maps B to C, and FOG maps A directly to C. Here you can see, for example, we have fx squared and gx 2x plus 1. So how you do it? We consider whole gx as x here, right? So when we say fgx equals to, instead of x here, we put whole here, right? So it will be 2x plus 1 as x squared, right? And opposite side, g of fx, in here we put the whole content of f. So it will be 2x squared plus 1. So this is the meaning of FOG and GOF. We can say FOG and GOF. If we have two functions of f and g, and they are defined as a set of integers, then f is 2x plus 3, and gx is 3x plus 2. What is the composite of FOG and GOF? Very simple. We put one in another one. So in here, instead of x, we will put gx. So in here, instead of x, we put gx, right? So fx is f of 3x plus 2. Instead of x, we put gx here. And so here, 2, this is g, right? Plus 3. And 2 multiplied 3 plus 4 is 6s plus. And other side, in g, we put f, right? G of fx. G of 2x plus 3. This is f. 3. And here we put f. It will be 6x plus 11. Simply, we can graph functions. How to do that? Very simple, right? X, y. if x is equal to 0, so here we have n, doesn't matter. You can say n, and here we can say f and same. So if it is 0, then what is that? 2 multiply 0 plus 1 is 1. If it is 1, it will be 3. If it will be 2, it will be 5. If it is minus 1, 2 minus 1 minus 2 plus 1 is minus 1. If it is minus 2, right, then it will say minus 3. So then here we say 0 and 1. This is n, this is fn. 0 and 1 is here. 1 and 3 is here. 2 and 5 is here. Minus 1 and minus 1 is here. And minus 2 and minus 3 is here. Right? This is above. For f squared, again, same. I told you already, right? X, fx equal to x squared. 0, 0, 1, 1, 2, 3, 9. Minus 1, 1, minus 2, 4, minus 3, 9. As you can see, 0 and 0, 1 and 1, 2 and 4, 3 and 9. Then you draw this line, everything is square. There are some important functions that we must know them. They are used in many places. The first one is floor function. Floor function is we round to the smallest one. 3.5 is if this is 3, if this is 2, if this is 4, if this is 5. 3.5 is something here. So we go to the smallest one. So floor of 3.5 is 3. Floor of minus, it is 0, 1, minus 1, minus 2. Minus 1.5 is here. This is the smallest one. We come to this part. Always the left side. And you can see the graph here. Ceiling is opposite. So in here we go for 4 instead, so the right side. In here we go to minus 1. So this is the ceiling function graph you can see here. We have some useful properties for floor and ceiling function. If we have n as integer and x as a real number, then floor of x is n if x is between n and n plus 1. The ceiling of x equal to n if x is between n and 1 less. The floor of n is between x and x minus 1, and you can see floor of minus x is minus of ceiling. Ceiling of minus x equal to minus floor, and you can see the other properties here. Factorial function, I think you already know it. Factorial means multiplication of all previous numbers, and it is defined for positive integers, not for negative. Factorial of 0 is 1. Factorial of 1 is 1. But factorial of 2 is 1 multiplied 2, 2. Factorial of 6 is all. 6 multiplied 4, 5 multiplied 4, 3, 2, 1. Which is factorial of 20 means 20 multiply 19 multiply 18 multiply 17 multiply 1, which is equal to this big number. And the last one is partial function. Partial function is a function that is not defined for some input of the right type, but a domain. For instance, division is a partial function because we cannot define the division of x divided by 0. It's called that partial. So a partial function from set of A to B is an assignment to each element A in subset of A, which we call them as domain of definition, or a unique element B in B. The set A and B are called as domain and codomain like before we have. And also we say that if F is undefined for element in A that are not in the domain of definition of F. When the domain of definition of F equal to A, we say that it is called as total function, and we show like this. For example, F gives n to R, and we have Fn equals to square root of n. It's a kind of partial function from Z to R, where the domain of definition is the set of non-negative integers. So here we should say that F is undefined for negative integers, for example, for -1 or -2. Okay, this was an introduction about functions. Thank you, and please feel free to ask me if you have any questions.